All right, this is Mr. Hendrickson here, and I'm going to give you a quick Postlab on the moving inertia lab here. While we're doing this, do take note, there are a few spots at the end here where you want to go ahead and fill in the note sheet for today. That note sheet can be found in our group in Schoology if you go to the Momentum folder, and then you're going to go down to Student Notes, and it's the second one in there, Notes, Conservation of Momentum and Explosions. Go ahead, grab that, throw it in your Notability. We'll go ahead and fill these definitions in here, and then there's going to be a follow-up lecture file that contains some example problems that you'll work as well. So go ahead, pause the video, take a second and grab those, and then when you're ready, you can fire the video back up. All right, here we go. Here's your Postlab. So if you'll recall back to last week, we did the explosion cart lab where at the very beginning we took some qualitative observations and we had the single cart. We pushed the button on the single cart and the plunger went out and, well, gosh, the cart just sits there. Okay, so when that's occurring, we have a whole bunch of internal forces. We have the spring pushing on the cart pushes on the spring pushes on the plunger pushes on the spring. These are third law pairs, right? Actions and reactions. Okay, but what we need to see happen here, folks, is we need an external force on the system. Okay, the cart with all of its parts here, the springs, the plunger, that's our system. We need something outside of the cart itself to act on it in order to get the cart to accelerate and change its momentum. Okay, in this case, there is nothing for the cart to push off of, so the momentum of the system is going to remain the same. Okay, so there was an absence of an external force. There was no external force, so the momentum of the system remained the same. Okay, before we pushed the button, the momentum was 0 initially, and after we pushed the button, the momentum was 0. So the momentum was unchanged. Okay, this is the law. We call this the law of conservation of momentum. There's no way around it. In the absence of an external force, the momentum of a system remains unchanged. Go ahead, take a second, pause the video, write that down in your notes now. All right, so now let's go to the two-cart system here. So this could be any one of the 8 trials that we did when we did the lab. We took the 2 carts, we put them together. We might have varied the mass on one of the carts so that we had 2 carts with 2 different inertias. And before we push the button, we noticed that the momentum of each cart is 0. Okay, we know it's 0 because we can calculate the momentum of anything by doing the inertia or mass times its velocity. Okay, well, we know in both of these cases that our velocity is going to be 0 meters per second. So in both cases, both carts have 0 momentum. So the momentum of our system before we push the button, before the explosion, that total momentum is going to be 0. Again, another way that we could write this or show this is we have 2 carts together. So the sum of the 2 momentums that are currently touching, they're together. They're one system. They're one object. The momentum of those objects together is 0 because they are not moving. Okay, now we're going to go ahead and we're going to push the button here, and our carts are going to push off of each other. Okay, when our carts push off of each other, right, cart 1 acts on 2, 2 acts on 1, and there are external forces on each individual cart. So each individual cart will have a change in momentum, right? Cart 1 speeds up to the left, cart 2 speeds up to the right. So what we end up seeing here, and you should have noticed this in your lab, is that one of our carts should have had a negative momentum. One cart should have had a positive momentum. Okay, so the way we're going to reference this here by looking at the page is we're going to say to the left is negative and to the right is positive, so that we see that cart 2 has a positive momentum because it was moving in the positive direction, and cart 1 has a negative momentum because it's moving in the, well, negative direction. Okay, so from there we can go ahead and we could calculate these momentums. We could take the mass times the velocity of cart 1 and find its individual momentum, and do the same thing for cart 2 to find its individual momentum. One thing you hopefully noticed as you did this lab was that as we lowered the mass of one object and raised the mass of the other, right, the velocities changed proportionally. So as our mass decreases here, we should have seen our velocity increase for cart 1, and the opposite happened for cart 2. As we increase its mass, its velocity decreased. Okay, but what we should have also seen here, okay, was that these momentums should have been equal and opposite. Okay, and how do I know that these two momentums should have been equal and opposite? Well, gosh, because I know that before we push the button, the total momentum of our system was 0. Therefore, the total momentum at the end should also be 0. So what we could do here is we could plug in our masses and velocities for cart 1 and cart 2, and we could sum them up, and hopefully what we end up finding out here is that the momentum ends up being 0. Now, I know when you did the lab, you probably didn't get exactly 0, but hopefully you got something close, okay? 0.1 or negative 0.1 or maybe even 0.0 something or 0.00 something, okay? There were plenty of sources of error within this lab that caused us to find a total momentum after the explosion that was non-zero, but in reality, it was pretty close to 0, and that's what we should have seen because, again, momentum is conserved. The momentum before we push the button was 0, so the momentum after we push the button, cart 1 plus cart 2, should sum up to 0. So if we go ahead and look big picture here, we're going to get a couple notes down in your note sheet. So let's go ahead and make sure we write this down here. So conservation of momentum says that the momentum before an event is going to be equal to the momentum after, because momentum is conserved. If we expand that out further to an explosion problem, okay, I want you to think of, we have two objects together, object 1 and object 2, they're stuck together like our two carts that are touching. Okay, we push a button, something happens, those two carts push off of each other, okay, and explode apart, okay? So in the end, we have two separate objects, okay? One object becomes 2. If we expand that equation out further, we could calculate the momentum of the singular object by taking the mass of the two objects, summing them up, and multiplying them by their common velocity, however fast that system is moving. Okay, here it was 0. In other cases, it might not be 0. That's okay. Okay, that's how we would find the momentum of the single object at the beginning. Then when that object explodes apart, it becomes two separate objects. So you would find the momentum of each object individually, and the sum of those objects would be equivalent to the momentum of the one object at the beginning. Okay, so take a few seconds, pause the video. Let's go ahead and make sure we have this all written down in our notes so that we can go ahead and perform some explosion separation problems here next.